Hiya! So in this video, we're going to continue talking about orthogonal operators, in particular linear operators satisfying certain constraints and kind of what they look like in 2 dimensions. So in a Euclidean vector space of 2 dimensions. So let's kind of look at this. So remember last time we had this lemma 171, which basically said if I have an orthogonal operator in E2, well, this is orthogonal if and only if the matrix can be written in the following form. So I have cosine, sine, cosine, sine, such that cosine of psi minus phi is equal to 0. Now, I said we would discuss this condition a little further. So what is this condition? So when is cosine 0 equal to 0? Well, cosine is equal to 0 whenever we have this thing on the right. So whenever we have this equality, pi over 2 plus k pi. So in other words, I need this inequality, or this negation, so psi minus phi, I need it to equal pi over 2 plus k pi. For some integer k, I don't really care what it is, but that's basically what it is. Now for us, what this is basically going to mean is that the geometry of the linear operator is going to be dependent on whether or not k is even or odd. And this is really going to be splitting our orthogonal operators into 2 classes. So one of the classes, right? So here it's when psi is going to be equal to phi plus pi over 2 plus 2m pi. Right here, what I require is that k is equal to 2. K is equal to 2m. So k is even, right? So here what I did is I took this formula here and I rewrote it as psi is equal to phi plus pi over 2 plus k pi. I said k is even, therefore we have 2m pi, and that's how we get the first one. So that's case 1. The second case is we have phi minus pi over 2 plus 2m pi. Well, where is this minus pi over 2 coming from? Well, here I'm letting k equal to 2m minus 1. So what happens if I let k equal to 2m minus 1? Pi over 2 plus 2m minus 1 pi. This minus 1 hits the pi and it brings this minus over. So pi over 2 minus pi plus 2m pi, which is why we get that equality. So here we have 2 cases, so let's look at them one at a time. The first case is going to actually give us rotations. So let's look at these rotations. And this is precisely when k is even. So when k is even, we have k is equal to 2 times m. In other words, what we really have is psi is equal to phi plus pi over 2 plus 2m plus pi, which is a mouthful. But what we can do is, okay, so what we're going to do is we're going to look at this a matrix here. So we have this matrix here, and we're going to try to look at this column in particular, cosine of psi and sine of psi. And we're going to try to reduce this as much as possible. So cosine of psi, we know what this value is equal to. This is cosine of phi plus pi over 2 plus 2m pi. Now the 2m pi, this is not really changing the cosine, so we can get rid of it. So you have cosine of phi plus pi over 2. Well, what is this? This is just nothing more than the minus sine of phi. Similarly, for sine of psi, doing the same thing, we get this is equal to cosine of phi. This is just messing with sines and cosines. These should be equalities that most of us are used to, or we can easily look up and remember. So what does this look like? So if I look at this first condition, so what do I have? So I'm going to keep the first column the same. So I have cosine of phi, right? It's cosine of phi, sine of phi. Remember, this is just cosine of psi, sine of psi, right? So this was the equality we had. But now I have the equalities above. So this is going to be cosine. I guess we can just do this. We can just swap these. So we can remove the cosine of psi. This is just equal to minus sine of phi, right? So this is cosine of psi. And here I'll put the note here right now. Sine of psi, well, sine of psi from above is cosine of phi. So in other words, we just have p of phi because we only have to look at one variable. And this is when k is equal to 2m. In other words, what we basically have is if I take some arbitrary vector, so here let's set some arbitrary vector x, xe1, xe2. Well, if I take these and I multiply them together, so what happens if I multiply these together? Cosine of phi, sine of phi, minus sine of phi, cosine of phi, times this vector, so x1, x2, x1, x2. This gives us precisely the following vector, x1 cosine of phi minus x2 sine of phi, x1 sine of phi minus plus x2 sine of phi. So this gives me this vector. In other words, if I'm applying my linear operator to this vector, what do I get? Well, I have this top one, which is x1 cosine of phi minus x2 sine of phi. This is in the first vector, so this is e1, plus x1 sine of phi plus x2 sine of phi. Wait, not sine. This should be cosine. Sorry, this is cosine of phi. I read the wrong one. I was like, wait, we can't have two sines. This is in E2. Another thing to kind of note is if I take this determinant, right? So what's the determinant of this? This is cosine squared phi plus sine squared phi. Well, what is cosine squared plus sine squared? This is just equal to 1. So this is the determinant. So in other words, the determinant is equal to 1. So the determinant is equal to 1. And so this preserves the orientation. Now, if you might have seen this matrix before, this matrix is actually a rotation matrix. In other words, what we basically have, a rotation matrix, this is rotating by the angle of phi. And we will look at an example of this in the following video. So for now, we will just see that this, by equations, this is rotation, or I'm saying it's rotation, but in the next example, we'll kind of really look at one and see this rotation happen live. So I will see you in the next video where we give an example of a rotation matrix. So see you then. Peace.